Okay, good afternoon. This is a makeup lecture for ECE 351. We were in lecture 4, and here we're talking about how you find the zero input response. I've actually backed up just a tad, as I usually do at the beginning of the lecture, just to remind us what we were doing. So we were talking about the zero input response of a difference equation, and just in the way of review on page 10, we had said we write the characteristic equation by setting the right-hand side of the equation equal to 0, and we solve for the roots, which are called the characteristic values or the eigenvalues. Then the case we've done already is we looked at the case where your eigenvalues are real and distinct. And we get these gamma sub i's, which are the eigenvalues. The gamma sub i's to the n are the characteristic modes or the natural modes of the system. Then for the zero input response, we just take the weighted sum of the natural modes. So now what's different today is today we're going to assume we have repeated roots, but we'll still be doing this step. This step is going to change a little bit because we have repeated roots. We'll have gamma to the n for one of the natural modes, and then the next one will be n times gamma to the n. And then we'll still find the zero input response as the weighted sum of the natural modes. So I'm going to go ahead now to where we left off, which was on page 12. So this is going to give us an example now where we have repeated roots when we're solving the characteristic equation. So again, in the previous case, the gamma sub i's were all distinct. Now we're going to say we have a characteristic root repeated r times. Now in the example we're going to do, r is going to be twice. They're going to be two replicas of the root. So that means in our case, we're going to take the characteristic modes. The first one is going to be gamma to the n, as it was before. The next one is n times gamma to the n, since r is equal to 2 in our case. In our example, we're going to go up to n raised to the first power times gamma to the n. In other words, we're going to stop right there. Because again, r is 2, so the highest power of n we take as the coefficient of gamma to the n is n times r minus 1, where r equals 2, so that just becomes n to the first power. All right, so let's do an example here now. So the question says find the zero input response. Remember, that's the thing called y0. Down here we'll call it y0. And the system we're given has this as its equation. Notice it's already in operator notation. So we kind of got to that step for free this time, right? And they give us some initial conditions. Remember, the initial conditions are going to be used to find the coefficients once we're at the last step. So in this case, the characteristic equation, remember, for the characteristic equation, you take the polynomial in E, rewrite it using the gamma variable. So instead of e squared, we have gamma squared. 6e becomes 6 gamma, and then 9, of course, stays 9. Now we're going to try to solve that for the roots, the gammas that are the roots. So if I factor this, I get gamma plus 3 times gamma plus 3, so that gamma equals negative 3 is a double root, right? The root is repeated 2 times, in other words. Okay, so our characteristic modes, well, the first one is just going to be that gamma value to the n power, as it was in our previous example. But for the next one, we have to take n times that gamma to the nth power, right? Because we need two distinct characteristic modes. We can't just use negative 3 to the n twice. Over here, I wrote a little note saying that's a likely test question. By that, I mean that I would give you some kind of a difference equation, and the question would be, what are the characteristic modes? I like to ask that just because it sort of forces you to break down the procedure into steps. Right? We solve the characteristic equations to get the gammas. We find the characteristic modes. then we write that the solution is the weighted sum of those two characteristic modes. So here's my first characteristic mode. This one's a little harder because it's split in two. N times the gamma to the n is my second characteristic mode, and the C's are the weights that we need to find using the initial conditions. Okay, so now I'm going to take this equation and repeat it using n equals -1. So I get y0 of -1. We know from the initial conditions up here that that's going to have value -1/3. So that was given, the initial condition. Let me write a little note here. IC, initial condition. Okay, then similarly, after I do that, and I'll look at that in a minute, then I'm going to do the same thing, but repeat the equation with n equal to -2. And so then I'll be computing y0 of -2, and notice that was a given initial condition up here. So here's my second initial condition. And now let's write what the equation becomes. So looking at this first equation now, using n equal -1 up here in this expression. So I have C1 times -3 to the -1, that's this part, using n equals -1. Then adding n times C2, -3 to the n. Well, n is -1, so instead of adding, effectively we're subtracting 1 times C2 times -3 to the -1, right? Okay, similarly for the second equation, but now I'm looking at this equation and I'm going to replace the n by -2. So now I have C1 times -3 to the -2nd power right here. And then the n becomes -2 times C2 times -3 to the -2, right? Again, there's my n value. All right, so that's a system of two equations and two unknowns. Of course, I would do the arithmetic to simplify it. Let me just kind of help you a little bit with the arithmetic. The -3 to the -1, that's the reciprocal of -3, so that's -1/3. Similarly down here, the -3 to the -2nd, that's going to be the square of whatever we had for -3 to the -1st. So that becomes 1/9, right? Because we're basically squaring something that's a negative number, it becomes positive. The fact that it's a negative exponent means take the reciprocal, so it becomes 1/3 to the 2nd power. Okay, and I think the rest of it then just becomes solving two equations and two unknowns. Any method, again, is okay. Kramer's rule, substitution, whatever technique you've learned. Trying to think of some of the other ones. Gaussian elimination, for example. Any technique you know for solving two equations and two unknowns. If you do that, you'll get C1, the first unknown coefficient, is 4. C2, second unknown coefficient, is 3. So remember, this was C1 times gamma to the n, and then we had C2 times n gamma to the n, and there we have our final solution. So that's our answer. Okay, in general rule, I won't solve the system of two equations and two unknowns in class. If you feel like you need help, be sure and come and see me in an office hour, and then I can give you some individual help with that. Okay, so now we're going to look at the third case. Remember, there are three cases on the gamma values. Either the gammas are real and distinct, that was case 1, or the case we just did, case 2, the gammas are repeated. At least one of the gammas is repeated. And then case 3 is, what if the roots are complex roots, right? And we're going to assume that the equation we're dealing with has real coefficients, because every time you model a real-world system, it will have real coefficients. So we can make that assumption. So the question is, write the roots, not the question. The question is basically going to be find the zero input response. So the way we're going to find the zero input response for this case, case 3, is we're going to write the roots of the characteristic equation in polar form. So I find the gammas. Remember, the roots of the characteristic equation, those are the gammas. Whatever those gammas are, you want to write them in polar form. And there's a little note here that says as long as you have real coefficients for your difference equation, and we always will, any complex roots always come in complex conjugate pairs. So that'll mean we won't have to think so hard to find the roots, right? So just as a reminder, if a plus bj is a root, so is a minus bj. Those are complex conjugates of each other. If it's in polar form, if re to the j beta is a root, then so is re to the minus j beta. Those are complex conjugates of each other. Okay? And then we're going to give you just a nice shortcut for finding the zero input response. We're not going to derive it. We're just going to claim that this is the answer. This is one you wouldn't be expected to memorize. I would allow you to write this on a study sheet and use your study sheet, because case 3 is sort of the most difficult case. And it's not a case, well, I shouldn't say that. It certainly can happen in practice. But in general, we wouldn't expect you to memorize the steps for this one. So you'll be writing notes for this. So the rule is that the output y0 of n, the zero input response due to the initial conditions, is c times magnitude of gamma to the n times cosine n plus theta. So notice that assumes that you've already got the roots in the complex conjugate form. The magnitude of the gamma here is that number r, right? The angle is the number beta. The angle equals the number beta, the angle of the complex root. So re to the j theta, that's the magnitude of gamma, and then the angle is going to be beta. Right. So then what's left in terms of unknowns that need to be determined from the initial conditions? It's going to be the c and the theta. The theta is the angle of the cosine. The beta is the angle of the root, the complex conjugate root, or it doesn't matter whether you say the positive beta or the negative of beta. Either way, those come from the roots of the characteristic equation. Okay, let's do an example. And remember, the little note over here says you could do the exact same technique we used for real distinct roots, but the arithmetic becomes really, really horrendous for complex numbers. So I wouldn't suggest that. I would suggest that you use the shortcut. Okay, let's do an example. So here's one where, again, we have the system equation. This is already in advanced operator notation. That means we're using the e's to represent advances. So like this means there's a term y to the n plus 2, right? This means there's a term y to the n plus 1, and so on. And notice they're giving us the initial conditions. So the characteristic equation, we just take the polynomial in e and rewrite it in terms of gamma. So it becomes gamma squared minus 1.56 gamma plus 0.81. That's the characteristic equation. Remember, the right-hand side of the characteristic equation is always 0 because we're killing off the input. Zero input means make this input x of n equal to 0, right? So now we have to solve that, and of course you can use your calculator. Calculator's okay. So I say use the quadratic equation or MATLAB or whatever technique you can use on your calculator to solve that quadratic equation. Notice we can't just look at it and solve it by factoring. In fact, it'll turn out to be complex roots. So it turns out that the roots are 0.78 plus or minus 0.45j. I've done some rounding already. And when you get that in polar form, it's 0.9 e to the j pi over 6, plus or minus. Okay, now how would you find that, though? Because again, that's sort of the meat of the problem, is how do you find the roots of that equation? So I'm going to run through the steps in MATLAB. Again, I realize a lot of you haven't had 309, so it's a little bit more difficult for you. But in 309, you learned that you can enter a polynomial by stating its coefficients. So this is the polynomial for the characteristic equation. And notice you just enter the coefficients. First term has a coefficient of 1, then a negative 1.56, and then a 0.81 for the constant term. Putting those in brackets means that's now, well, of course it means it's a vector, but MATLAB knows now, the minute you ask for the roots of a vector, it knows that you mean those to be the coefficients in some polynomial, right? Because it only makes sense to ask for the roots if you've got some kind of a function. In this case, we're describing the polynomial function via its coefficient. So square brackets and then round brackets for the roots function. Square brackets to define the polynomial, roots parentheses to find the roots of that particular equation. And notice MATLAB gives you these nice two complex conjugate roots. Notice because of the signs here, they are complex conjugates. Now the trouble is we need it in polar form. So now we have to tell MATLAB, remember if I were writing in this in the form a plus bj, the a number would be 0.78, the b number would be 0.449. So I need to use a function called cart to pole. Cart to pole means Cartesian, meaning rectangular, to polar. So it's going to change the rectangular coordinates A and B. And notice I've done some rounding again. A I'm saying is 0.78. That's okay. But over here I've rounded 0.449 for the B to make it 0.45, just to save space, really. So those are my Cartesian coordinates. Right now these are Cartesian, meaning A, B, or XY form. And notice you don't put in the J or the I, you just put in the coefficient of J or I in the second position here. If you're using the function cart to pole, if you want the angle and the magnitude of the polar form answer, angle and magnitude, you have to specify what are you calling the angle, well I called it theta, and what are you calling the R, the magnitude. So I gave it names. It's a little bit confusing. Maybe I wish I kind of hadn't called it theta because there's another theta in our equation. I probably should have called it beta. Beta would have been a better name for it. Okay, so better call that beta. That's really what it is. And then here MATLAB would spit back the answer. The beta value is 0.523. So again, I asked MATLAB for changing Cartesian coordinates to polar coordinate, and I tell it specifically what I'm going to call the angular part of the answer and the magnitude. Okay, so you have to name them something, in other words. Okay, so it gives me that the beta is 0.5233. That's, by the way, in radians, right? Typically, we want to change that to degrees. So down here, I'm going to do a command that says beta in degrees, beta degrees, is whatever we had for beta, the original beta, multiplied by 180 over pi, because of course that's how we change radians to degrees. We multiply in a 180 over pi. And then it's going to give me the answer that, oh, the beta in degrees is 29.98. I'm going to round that off to 30 degrees, okay, which is about pi over 6. Okay, so again, I asked MATLAB for the roots of the quadratic equation. I changed them to polar form with cart to pole. Then I changed the angular part of the answer to degrees, So here's my beta in degrees. And notice it gives me that r is about 0.9. So again, I rounded that to roughly 0.9. So now you see where I'm getting this answer, 0.9 e to the j pi over 6, right? So where the beta answer here is pi over 6 in radians or 30 in degrees. Okay? So now this is what our answer looks like. Remember, the standard form of the answer coming from the previous page says you take the unknown c, that's one of the things we're going to be looking for. You take the magnitude of gamma to the nth power. So the magnitude of gamma, that's the thing we called r. It's 0.9 roughly. And then this is cosine beta n plus theta. And so the things that we don't know right now are we don't know this constant c and we don't know this angle theta. Right? By the way, that's again why I changed the name of the angle up here to beta. So I'm trying to be clear that it's two different numbers. Okay. Page, doesn't matter if I erase stuff. So remember that we had, oh, I'm sorry, it does matter, but okay. I guess I better explain this part again. I made a mistake. My bad. I made a mistake by going forward and backwards. So let me kind of re-explain this page. I just did it, but then I went forward and backwards and erased it. So let me repeat this part. Y0 of n is c times 0.9 to the n cosine pi over 6. Remember, this was my gamma magnitude to the n. This was my angle that we called beta, and we had these initial conditions were given. So first thing I'm going to do is I'm going to take this equation letting n equal -1. And if I do that, I'm going to get y of -1, which according to the initial conditions should be 2. Then I take the equation up here and rewrite it using n equal to -1. So this n is going to become -1 down here. The n here becomes -1, so I'm going to get negative pi over 6, and theta, of course, stays theta. Then I simplify this by saying 0.9 to the -1, that's just 1 over 0.9. That brings me down here to c over 0.9. Now, I also need to do something with this cosine negative pi over 6 plus theta. And what we're going to do is we're going to write this as cosine a plus b. And there's a trig identity that I'm going to write at the bottom here. Cosine of a plus b is cosine a cosine b minus sine a sine b. And you don't need to memorize that. You would have that written on your exam sheet. So I'm going to use that now to break apart this cosine a plus b into cosine a cosine b minus sine a sine b, where I've used a as negative pi over 6 and b as theta. Okay, so then I take the c, write it as c over 0.9 because 0.9 is the negative first. This is now just a number. Cosine of negative pi over 6 on your calculator is root 3 over 2. Over here, I have the negative of sine negative pi over 6. Again, that's a number. When you throw in the negative sign sitting in front with the sign of negative pi over 6, it becomes the number 1/2. Be real careful when you do this. Caution that the calculator is in radian mode, not degree mode. Okay, so every semester several people get these problems wrong because they haven't done enough practice and they're not very careful about which mode their calculator's in. So if I want the sine of negative pi over 6, I need to know that the pi over 6 is measured in radians, so I have to make sure my calculator's in the right mode for that. Okay, we're going to give this equation a name. I'm going to call it 1, and we're going to come back to that later. Then I want to use, so now I've used up the first initial condition. Now I want to use the second initial condition when n is -2. And we know the numerical value should be 1. That's my initial condition. So I take this equation again and use n equals -2. So on the right-hand side, I have c over 0.9 to the -2 times cosine, remember now, pi over 6 times n, but n is -2. So if I double pi over 6, I get pi over 3. And since n was -2, it becomes -pi over 3. And then I have plus theta. So that's using my initial conditions. Now I'm going to actually do the arithmetic. Again, this is A, this is B, and I'm going to use that trig identity. So it becomes cosine A, where A is -pi over 3, cosine B, where B is theta, minus sine A, sine -pi over 3, and then sine B, which is sine theta. And then again, simplifying, the coefficient in front becomes c over 0.9 squared, or c over 0.81. This is now just a number. Cosine -pi over 3 on your calculator is 1/2. This one's just a number. Cosine -pi over 3. That's the number √3 over 2. All right, but again, when you throw in the negative of sine -pi over 3, you get positive √3 over 2. Okay, give that equation a number and call it number 2. And we're going to carry these two equations now forward. Equation 1 and equation 2 are going to move forward with us. Here's equation 1, here's equation 2, just repeating. Okay, so I just repeated the equations, and actually I rewrote the form a little bit, so it's not exactly true that they're exactly literally the same. I did a little bit of the arithmetic, which you'll be able to follow pretty easily. But the point is, what I have here is I have some number times c cosine theta plus some number times c sine theta equals 2. And in the next equation, I have some number times c cosine theta. Notice that's the same term. And another number, different coefficient, times c sine theta. Again, those are the same terms, equals to 1 on the right-hand side. So what we're going to do is we're going to treat these as two equations in two unknowns. Now, you may say, well, that's obvious. There's a c and a theta, which are the unknowns. And that's true. But we're not going to treat it as if c and theta are the unknowns. We're going to group this together. C cosine theta, treat it as if it's a big old variable called x. C sine theta is another big old variable called y. The reason being that if I just look at that equation in c and theta, it's not linear algebraic, right? It's not a linear algebraic equation. But if I change c cosine theta to x and c sine theta to y, then I do have a linear algebraic equation. X and y are algebra variables, right? So down here also, I take c cosine theta, that's x, c sine theta, that's y. So I'm going to treat that as if it's two equations in the unknowns x and y. And then I'm going to solve them, just as I would for any other x and y. And again, that's well below the level of this course, so that's just you solve the same way you solve any system of two equations and two unknowns for x and y. And you'll get 2.3 roughly is the x value, negative 0.4 roughly is the y value on the right-hand side. And now the trick is, how do you get rid of the fact that we've kind of mushed the variables together? C cosine theta and c sine theta, those really weren't the variables we were after. So what we're going to do is we're going to find the tangent of theta by taking c sine theta over c cosine theta. Now obviously the c's would cancel, and you'd get sine over cosine, which is tangent. That's correct. But the point is, we knew a numerical value for c sine theta from up here. And we have a numerical value for c cosine theta right there. And if we plug those in, the arithmetic becomes negative 0.172. So we're better off by kind of combining the variables into new variables called x and y. Okay, now you might look at that and say, well, gee, that's fine, but I still don't know what theta is. But if we know the tangent of theta is negative 0.172, if we take the arctangent, then we're going to get theta is the arctangent or the inverse tangent of negative 0.172. Turns out to be about negative 0.17 radians. Okay, now we also have the fact that we know what c cosine theta is. Now we plug in the fact that theta is negative 0.17. Right? So we find the cosine of negative 0.17, in other words, and we solve for the number c. And it'll turn out that c is roughly 2.34. So remember our equation, we had c, and then we had magna of gamma, which was 0.9 to the n, and then we had cosine beta n plus theta. So here's now our theta is negative 0.17. Our beta, of course, was the pi over 6, and the gamma was 0.9. Okay, so that's it. Now we have the entire zero-state response. I'm sorry, zero input response. Okay, zero input means we've killed off the input. Okay, let's try a practice problem here. This practice problem says find the zero input response if y of n plus y of n minus 1 plus 0.25 y of n minus 2 is root 3 x of n minus 1. So the first problem is that right now this is in what we call delay form. And we really need it to be in advanced form, and then we can go to advanced operator notation before we can find the zero input response. So let's write it in advanced form. And remember, the way we do that is we look for the most that's ever subtracted, which is right here. The capital N value, the order of this difference equation is capital N equals 2, because that's the largest value subtracted from the nominal index of n. And so now what we do is we say, well, I'm going to replace n by n plus 2, because I want it to be in advanced form. So my equation becomes y of n plus 2 plus y of n minus 1. I'm looking at this equation here and replacing n by n plus 2, plus 0.25 y of n equals square root of 3x of n plus 1. Okay, so I replaced all n's by n plus 2. Okay, so the question is, first write it in advanced operator form. So I'm going to take this now and write it in advanced operator form. So that's going to be e squared plus, I'm sorry, I have a right-o here, a mistake. This y of n minus 1 became y of n plus 1, right? There we go. So e squared plus e plus 0.25 acting on y of n equals, and then since I'm looking for the characteristic equation, well, let me go ahead and complete this. Square root of 3 e x of n. Okay, so that's just using advanced operator notation. Now I'm going to write the characteristic equation in gamma, so this becomes gamma squared plus gamma plus 0.25 equals 0. Remember, you always kill off the x on the right-hand side. Now we try to solve for the gammas. So in this case, I can solve. I get gamma plus 1/2, gamma plus 1/2 equals 0. So if I solve it, that would imply that the gamma equals negative 1/2. So our characteristic values are negative 1/2, negative 1/2. But our characteristic modes, one of them is negative 1/2 to the nth power. The other one is going to be n times negative 1/2 to the nth power, right? You can't use negative 1/2 to the n 2 times. So our zero input response is going to be some constant times that first characteristic modes, negative 1/2 to the n, and some other constant times the second characteristic mode, n times negative 1/2 to the n. Okay. Okay, now, so far we had this, and now we need to finish this problem, find the zero input response. So what I need to do now is I need to say, well, this equation comes, or this initial condition comes about when n is negative 1. So I'm going to use n equal to negative 1 to get a numerical value of 1. And then now I put n equal to negative 1 up here. So we get, I'm sorry, I drew that in the wrong spot. Let me see if I can erase that. Eraser. There we go. Try that again. Okay, so I want to put n equal to negative 1 in this equation, right? And so I have already that the y0 of negative 1 is 1. But now I want to look at the right-hand side of the equation. So what have I got? I've got c1 times negative 1/2 to the negative 1 plus c2, and then an n, where n is negative 1, is going to make this a minus sign sitting out in front, and we're going to have negative 1/2 to the negative 1. All right. And if I now go to using up the second initial conditions, y of 1, so I'm going to use n equal to positive 1, the numerical value on the right-hand side will be 1 again. But on the left-hand side now, again, I'm going to this equation, and I'm going to plug in n equal to 1. So it says c1 times negative 1/2 to the first power, which is just negative 1/2, plus c2, and then a 1 times negative 1/2, again to the first power, and that should equal 1. Okay, so let me take those two equations. Let's call this equation 1, similar to what we did before. Call this equation 2. And let me simplify equation 1 now. Equation 1, when I take the reciprocal of negative 1/2, I get negative 2 c1. And again, taking the reciprocal of negative 1/2 gives me negative 2. With a minus sign here, though, it becomes positive 2c2, and that should equal 1. Okay, on the second equation, again, just simplifying the second equation, there's not too much to do on this one. We're going to have negative 1/2 c1, negative 1/2 c2 equals 1. Okay, and I'm going to do this in the form like ax plus b, where the a is the coefficient matrix. And so my coefficient matrix A in ax equals b, the A matrix would be negative 2, 2, and then negative 1/2, negative 1/2. And then the B would be this vector over here, 1, 1. That's what the B vector is. So here I'm entering in MATLAB the A matrix. So that's the A matrix. Then this is the B coefficient vector, written as a column vector. And when you do this little backslash, it really means you're doing x equals A inverse times B. It's kind of a weird way of doing it, but that's what MATLAB does. Okay, so here's my code. The answer MATLAB gave me for the C1 and the C2 are -5/4 and -3/4. So here's my C1 value is -5/4. My C2 value is -3/4. And here's my gamma to the n, and here's my n gamma to the n. All right, so that's it. That's my answer. And let's go forward again. So let's just summarize what we've done here. Like in this lecture, we compared how you find the Y0. Remember, that's zero input response. Zero input response. And we showed how we did it just in the way of review for differential equations. And then we said, what's different? How do we do it for difference equation? So for differential equations, you write it in the form Q of either the D or the S operator acting on Y equals polynomial P of D or polynomial P of S, if you want to use S for the operator. And then that operator is acting on X. In this class, it becomes Q of E acting on Y equals P of E acting on X from the advanced operator notation. Okay, on the left-hand side in 350 class, you wrote the characteristic equation Q of lambda is 0, where you just replace the D's or the S's by the lambdas, and you set the right-hand side equal to 0. Well, that's really what we do here too, except we're replacing the E's, the operator notation, by gammas, and again, setting the right-hand side to 0. The eigenvalues on the left-hand side were called the lambdas, the roots of the characteristic equation. In this class, we call them gammas. You find the natural modes, which were, I'm only doing case 1 here in the summary. Case 1 for real and distinct roots. The characteristic modes were e to the lambda I t. In this case, they're just gamma sub I, for the ith root, to the nth power. And then in your other class, in 350, you said, oh, the zero input response is just the weighted sum of the natural modes. Well, that's exactly the same as what we do in this class. And then you find the unknown constants, the c sub i's, the coefficients using initial conditions. That's exactly the same. So really, this is like probably 80% the same as what you did in your 350 class. Okay, so hopefully you learned that really well in 350. Let's do a quick review question, and then we'll cut this off for this lecture at least. So this question is, write in advanced operator form, then change to operator notation. So this is right now in delay form. So we add 2. Again, this tells me capital N equals 2, because that's the biggest number subtracted from the nominal index of n. So I'm going to add 2 everywhere, y of n plus 2, plus 5y of n plus 1, plus 6y of n equals 4x of n plus 2, plus x of n plus 1. Let me just double check that. Okay, y of n became y of n plus 2, y of n minus 1 became y of n plus 1, y of n minus 2 became y of n, x of n became x of n plus 2, x of n minus 1 became x of n plus 1. Okay, that looks good. So now we have to go to the operator notation. So this would be e squared plus 5e for this term, plus 6, no operator for that last term, all acting on y of n. On the right-hand side, we have 4e squared plus e, all acting on x of n. Again, let's go back and check. This one became e squared, this became 5e, this became just plain old 6. On the right-hand side, we had 4e squared plus e. Yep, looks good. Okay, so that's what we mean by operator notation down there. All right. Then it says write the characteristic equation and find the natural modes. So characteristic equation is going to be gamma squared plus 5 gamma plus 6 equals 0. Taking this and replacing the e's by gammas. On the right-hand side, I set the right-hand side equal to 0. So I solve this. Well, factor first. Gamma plus 3, gamma plus 2 equals 0.